Welcome everyone, I'm Mariana Gomes and I will present my paper titled Multiscale Method, a powerful tool to reduce the computational cost of a big data problem involving stick-slip oscillations. The paper has been co-authored by Roberta Lima and Rubem Sampaio. I will begin by talking about our motivation to study analytical approximation and its advantage. We apply this method in a system with direct friction, so I will describe the system and its dynamics. Secondly, I will talk about the multiscale method, which was used to calculate the analytical approximations. Next, a comparison of CPU time employed to perform the Monte Carlo method in a numerical and analytical approximation is discussed. And finally, I will talk about the conclusions. In this paper, the parametric study of a stochastic nonlinear IVP is performed by means of a Monte Carlo simulation. The paper analyzed the influence of 320 combinations of two parameters, lambda, that is related to the Poisson process, and μ, a friction coefficient. For its combination, 2,000 realizations are calculated, which means that in total 640,000 integrations were made. Performing all these calculations sequentially would require 2.5 years. Alternatively, the authors employed a parallelization strategy. The problem was solved by using 16 computers and the actual calculation time was 55 days. What motivates this work is that we know that even with parallelization, the computational cost remained high due to the numerical integration. This is a recurrent issue in the modeling of many physical problems that require the solutions of IVPs. In general, nonlinear IVPs do not present a non-analytical solution, which is why it is common to use approximation methods. Numerical methods have been widely applied due to their non-occurrence and to the fact that there exist many easy-to-use computational packages for their implementation. They allow a deeper understanding of how the solution depends on the problem parameters. In this paper, we use the multiscale method to compute analytical approximation. The main idea of this method is to transform a nonlinear IVP, which we don't know how to solve, in a family of linear IVP with non-analytical solutions. The system considered is composed by a spring, a damper, and a mass that moves over a belt with constant velocity v, as shown in the figure. There is a direct friction between the mass and the belt, and the equations that govern the dynamic system are shown in the box, where m is the mass, epsilon is the perturbation parameter, gamma is the damping coefficient, k is the spring constant, and Fat is the friction force, and R and B are the initial displacement and velocity respectively. The direct friction force depends on the relative velocity v. The system response with direct friction is composed by two phases, stick and slip. The stick phase is characterized by a period in which the relative velocity between the two bodies in contact is zero. In our problem, this means that the mass and the belt move together. During that period, the friction force assumes values between minus Fe and Fe. In this case, the friction force compensates the forces produced by the spring and the damper. At some point, the force produced by the spring and the damper surpasses the maximum value that the friction force can take. Then, the system enters in the slip phase, in which the relative velocity between the mass and the belt is not zero, as shown in the slide. In this figure, we show how the phases alternate. The sample shows the case of a response that starts with a stick phase. Note that stick and slip phases alternate abruptly and they do not have a zero duration. When the system is in the stick phase, the relative velocity is zero, so the mass and the belt have the same velocity v and acceleration equal to zero. So, for this phase, there exists an unknown and very simple analytical solution. But when the velocity is different than zero, the system is in the sleep phase, which is governed by the nonlinear IVP, for which we don't know a non-analytical solution. So for this phase, we use the multiscale method to obtain an analytical approximation to the solution. We present here the nonlinear IVP to which the multiscale is applied. The main idea of this method is to transform a nonlinear IVP in a family of linear IVP. The nonlinear IVP is modified by adding a perturbation parameter so that when it takes the value of 0, the equation is linear. Then a solution in the form of a sum of terms that includes power of a perturbation parameter is proposed. This proposal is introduced in the modified equation and the final solution is obtained by algebraic manipulation. Now that we have an expression for the analytical approximation, we can perform the Monte Carlo simulations. The Monte Carlo method is an important tool used to construct a stochastic model of random object transformation. To obtain a current statistical model, usually several samples of the transformation output are required. For the simulations, we consider the initial displacement as a random variable with a beta distribution. We fixed the parameter beta equal to 2 and chose 22 different values for alpha between 1.5 and 8 with support 0 to 2000. It is important to remark that the shape of the PDF changes with alpha, as shown in the present figure. So, for the values of alpha closer to 1.5, there is a higher probability of having values of R below 100, while for alpha equal 8, there is a higher probability of having values of R above 100. To compute the numerical approximation, we use the Runge-Kutta method of 4th and 5th order. The integration range is between 0 and 100 with a step of 0.1 seconds. Note that the time step employed in the simulation may be too high to get the transition instance with accuracy. This is justified in the fact that performing all the numerical integration of this work takes a long time, even for the chosen time step. The results obtained here serve the purpose. The focus of the paper is set on improving the CPU time, and they suffice to show that a great difference exists between the results of the two approaches. On the other hand, performing a Monte Carlo simulation falls in the category of big data problems. If you want to keep the results in memory of the simulations for every time step taken, for example, for post-processing, the amount of information that can be generated by the simulations is limited by the available memory. In this study, 22 Monte Carlo simulations are performed, each with 10,000 realizations. Again, the number of realizations is enough for the purpose of comparing the CPU time. The solution was parallelized using 28-core processor. This graph shows the required CPU time for the analytical and the numerical approximation. The parallelized numerical calculation took almost 14,400 minutes, while the analytical approximation took 11 minutes. We can also see that the time required for the numerical integration also shows a dependence on the value of the parameter alpha, which is not seen in the analytical approximations. Now the conclusions. The Monte Carlo simulations can require a high CPU time if numerical integrations are performed. Moreover, they fall under the category of big data problems. A large amount of information is generated due to the number of simulations required. And the numerical integration is sensitive to the value of the initial conditions. It is more time costly depending on the value. This is due to the fact that a small time step is required to calculate the phase transition instance with sufficient accuracy. And there is an important difference in magnitude between the analytical and numerical approximation CPU time. And another important advantage is in a numerical integration approach, the results are obtained at times that include the transition instance as well as intermediate point. Dropping any of those values would result in a loss of information and in a loss of accuracy in the solution. And with the analytical approach, only the transition instance and the solution at each one of them needs to be saved. Any intermediate time can be calculated directly and with the same accuracy of the original calculation by using of the unknown analytical approximation. So, thank you everyone for your attention.